So now that we've got the basic idea of what an integral is and what kind of things it can be used for, we're now going to start talking about a lot of different techniques for finding difficult integrals. So these are called, methods of integration, or sometimes a technique of integration, right? Sometimes they're called techniques, So we'll talk about various techniques of integration. A lot of Calculus 2, second semester, is taken up with various techniques, usually in most universities. All right, so as usual, I like to start with an exploration activity. Let's start with something that you could figure out just using sort of your common sense and your knowledge of derivatives. Can you find an antiderivative for each of these three functions? So go ahead and have a look at those. Take a pause on the video and see what you can figure out might be a good antiderivative for those. All right, so hopefully you've taken some time to figure that out. And because we've done some that are similar to this. All right, so when you see something like this, something you might consider is, what's the derivative of just cosine of x squared? All right, so I would start with that. And it's sort of like, let's leave this out of the picture for a while and say, all right, what's the derivative of cosine of x squared? Especially if you think, if I did the derivative of cosine of x squared, I would get 2x as the derivative of the inside function, right? So I would do, actually, I don't want to start with derivative of cosine x squared. That's wrong, because that's going to give me negative sine of x squared. I want my derivative to come out to be this. So instead of starting with cosine, I'm going to say, what's an antiderivative for just cosine? And just keep that inside function the same like we would do for chain rule. Chain rule is involved here, but this is not really a chain rule at all. So I wrote the same thing again? Come on. All right, so what's the derivative of sine of x squared? It's what we should really be thinking of, because the antiderivative of cosine is sine. All right, so what that derivative is, I would do the derivative of the outside, which is cosine. I would keep the inside function the same, that's x squared. And then I would multiply times the derivative of the inside function, which is 2x. And lo and behold, the derivative of sine of x squared turns out to be 2x cosine of x squared. And that's what I wanted an antiderivative for. All right, so what I can say here is, and our new idea of writing an indefinite integral is really handy if I want to just say what the antiderivative is, but I don't want to sit there and figure out an actual numerical value. So what I can write is the integral of 2x cosine of x squared dx is just equal to whatever I took the derivative of, sine of x squared plus c. All right, the reason for that is the derivative of sine x squared is 2x cosine of x squared. So the antiderivative of 2x cosine of x squared is sine of x squared. And remember, we put the plus c because it's an indefinite integral, meaning I could have c, any constant here, and if I take the derivative of sine of x squared plus any real number, that derivative, since the c is going to go away, is still going to come out to be this 2x cosine of x squared. So every function has infinitely many antiderivatives, and we represent that with the plus c. All right, so how about the x cosine x? Well, so I already know that the derivative of sine of x squared is equal to 2x cosine x squared. All right, so I already knew that, but I want the derivative of something to not have a 1/2 here. So what I do is I could just multiply both sides of this equation by 1/2. Right, just multiply everything times 1/2, and then I'm going to find out that the derivative of 1/2 sine of x squared is going to be equal to, the 1/2 is going to cancel the 2, it's going to be x cosine of x squared. All right, and that's what I wanted to have an antiderivative for. So now know that the derivative of 1/2 sine of x squared is equal to x cosine of x squared. So that means that the integral of x cosine of x squared dx is equal to 1/2 sine of x squared plus c. All right, so that is an exploratory method to get that antiderivative. Now, if I look at this one, it's a little bit trickier because I have this x cubed and this x squared, but I could still think about the idea that how this worked is, out here I have essentially the derivative of the inside function. Now, in the first case, what I had out here is exactly the derivative of the inside function. In the second case, what I had out here was not quite the derivative of the inside function, but it was a constant multiple of the derivative of the inside function. It was 1/2 of that derivative of the inside function. So I should be able to work with that. So let's think about this one the same way. What would be the derivative of, so again, I'll think of the antiderivative of cosine as sine, and I'll just keep the inside function the same. What would that derivative be? Well, it would be the derivative of the outside function is cosine, keep the inside function the same, times the derivative of the inside function, which is 3x squared. So that derivative is 3x squared cosine of x cubed. All right, but I don't want the 3. That's my problem. I have the x squared cosine x cubed, but I don't have the 3. So I'm going to pull the same trick we had here. Let's get rid of the 3 by saying, all right, this is what derivative of sine of x cubed is. So I'll just multiply both sides of the equation by 1/3. And then I will get that the derivative of 1/3 of sine of x cubed is equal to, the 1/3 will cancel with the 3, and I'll have x squared cosine of x cubed. So indeed, the derivative of 1/3 sine x cubed is x squared cosine of x cubed. X squared cosine of x cubed, that's what I wanted. So I can say that the integral of x squared cosine of x cubed dx is equal to this one plus c, 1/3 sine of x cubed plus c. All right, now we just got these derivatives by what could be called an exploratory method. I'm just saying, like, let's try some things and then modify what I get. It's almost like a guess and check type method. So what we would like to do is formalize this so that we don't have to do a lot of guessing and scratching out and rewriting. We can just get it in one shot. That is what substitution is about, and I will demonstrate that method starting in the next video.